Now, the next keynote is going to be provided kindly by Gavran of Informal Systems. Now, he'll be speaking about thinking hard is not enough. And as far as I've understood, he will speak about Quint, a modern specification language. Yes, difficult word indeed. And about different types of tools that fundamentally augment our reasoning. So that sounds slightly mysterious, but I'm sure it's going to be absolutely interesting. Let me just double check if there's one mysterious chair left. Please put your hands together and welcome once again on stage Gavran of Informal Systems. Yes, thank you. Thank you very much. Ivan, thank you for being here. Please take it away.
Thank you for the kind introduction. Hello, hello Split, hello world, hello Cosmos. Good to be here, good to see you all. Today I would like to discuss how we go about building software, particularly blockchain and distributed software, in the year 2025 and in the future. My goal is to offer a way to go beyond best effort approaches, especially in the context of AI-assisted development. But before diving into the topic, let's get to know each other. My name is Ivan, and I come from Informal Systems. At Informal, we do security audits using formal methods, and that's my personal background too. We also do a lot of building and deploying. So we built Malachite, a Rust consensus engine that is a very popular choice for modern L1s. We also validate for many chains, and we incubated two very, very exciting applications, Cycles and Hydro. You will hear more about them in the conference. So in short, we are all about building reliable distributed systems. How about you? What do you do? Show me a hand if in the last year you were writing code. Okay, very good. How about writing specifications? And I mean formal and English, both counts. Okay, some. Working on understanding users' problems, meaning defining features to implement, bugs to address. Very good. Reviewing code of your colleagues. That's blockchain. How about using LLMs for all these tasks? Very good. So I think we have a very good fit for today's topic, which at its heart has software engineering. And it goes beyond coding. And that's why I was asking these broader questions. Because smarter people than me have already concluded many times that the true value of software engineering is about aligning teams of humans around a good technical solution to a real-world problem. And with that idea of value in mind, let's look at the simplified pipeline of software engineering. So it all starts with humans, and these are users and people working on understanding users' problems. And then from there, we write English specifications. But this is then a very broad term. So it can be what needs to be built, how it should be built, what technologies to use, all the way down to architectural sketches and pseudocode. After that, we implement it in code, and then finally, where appropriate, it gets compiled down to a binary. And notice here one thing, that the arrow from the code to the binary is a straight one, because this is a straightforward, non-problematic process, whereas other arrows are these squiggly lines representing messy processes. And thinking about value being aligning humans, what is the most important artifact here? What is the artifact that aligns humans? It is code. And this is not even controversial. I mean, all of us, we version control our code. We also care that it's well organized, that variable names make sense, that there are comments at potentially problematic and confusing places. And we do that because we care that our thinking process is reflected in the code. That when we come back to it 3 months from now, that we understand what we meant, and that our colleagues reviewing the code, that they also understand what is behind the code itself. A naive question would be, but why code? Why not English specification? After all, it is high level, intuitive, and understandable for more people than the code. And therefore, it aligns more people around itself, so why not English? Code has some important advantages. It is that it's precise and executable, which enables lots of tooling built around code. Because of this tooling, we get a self-improvement loop inside the code. So in the development process, it is not that we just implement the English specification, but with the usage of these tools, we improve our understanding of what the problem is and what the solution should be. And therefore, soon enough, the code is better than the English specification, and soon enough, the specification goes obsolete. And then something happened. With LLMs, English becomes executable, and this opens many possibilities. So our first attempt was vibe coding. It's a lot of fun, but you know it, I know it, and the internet knows it, it's a mess. And I don't want to be overly dismissive here. It works amazingly well for some well-scoped tasks, but as soon as problems become bigger, it doesn't perform as well. But even if it did, even if it performed wonderfully, we get this conceptual confusion then, where we have a code that we are not intimately familiar with anymore, we have prompts that we threw away, and so this aligning idea is lost. And people have understood that is a problem, and that's why now everybody is doing spec-driven development. And every major player in this AI-assisted coding area has embraced the idea. And the idea is simple. We start from a very detailed markdown specification, and that's still a natural language with some pseudocode perhaps, with some examples of executions. And then we generate code. If we are not happy with the result, or if we want to add a new feature, we do not touch the code, but we modify the spec again and iterate on that. So we are now going from this situation of the pipeline to this one, where English specification attempts to be a major player because it gained some executability with an asterisk. It's a kind of executability because this line is still the squiggly one. And that makes sense. The idea makes sense, but of course it has some problems. So let's talk about English specifications, when they work and when they do not work. So I took these couple of examples from the internet with people posting and showcasing their successes using spec-driven development. It's a tic-tac-toe and a calendar. And what do these two applications have in common? The first one is, it is very easily clear if we got what we wanted or not. So we just play a bit of tic-tac-toe and understand whether it is what we had in mind or not. The same with calendar. The second one is that there's a lot of context already on the internet, what tic-tac-toe is and what a calendar is. And therefore, LLMs have a lot of context already, even before we write them what to build. But as soon as we go more towards custom problems, we get into problems. So one problem of English specification is that they're ambiguous. So what is 6 divided by 2 multiplied by 2 plus 2? It can be any of those. And of course, this is a toy example. It's immediately clear that it's ambiguous. But what would very often happen is that we would write something, we would think it was clear, but it would actually be ambiguous and not clear what we meant. English specs can also be internally inconsistent. So a triangle with 5 equal sides and a round corner, and make sure it's perfectly square. What is that? That's nonsense. But it is also a valid English specification. And there's nothing to stop us, and even worse, with LLM's infamous can-do approach, they would confidently produce a solution and argue for why it is the best solution. And so these problems are minor for some use cases, they're a bit bigger for the others, but they're absolutely the worst for blockchain systems. Why is that? The reason is twofold. At the application layer, blockchains deal a lot with assets, voting powers, numerical values, documents, identities, and therefore they cannot be roughly correct, or they cannot be 95% correct. They have to be correct. And the second reason is the underlying infrastructure layer is a distributed system. And when reasoning about distributed system, when specifying it, we not only have to specify what is the outcome of the computation, but we have to talk about the computation process itself. We have to talk about the topology of the network, assumptions on the message reorderings, what happens if in the middle of computation some node crashes, or what happens if a node goes Byzantine, meaning that it starts sending messages, arbitrary messages, or even adversarial messages to its peers. And the problem with that is the state space grows so big that we cannot fit into our head and we cannot reason about it the way we used to. And the edge cases that we are so rare that they won't be noticed by testing the implementation either. We will notice them only when it's too late. This is a good case. In a bad case, an attacker will notice them. The root cause, again, is the large state space that defies our thinking capabilities, or LLM's thinking mode. So our typical approach, let me think hard and notice problems, is not going to make it. And that's why we are building Quint, a tool that helps us thinking about specs. So let's see how Quint looks like. Quint is precise, just like code. These expressions probably look familiar to you. They're like code, but they reside on a higher level of abstraction, like English. It is also executable in a good old-fashioned way, and it's battle-tested on a number of blockchain protocols. So what can Quint do for us? Beside regular things like other programming languages, parsing, typing, type checking, writing tests, Quint can answer some higher-level question. Is my spec internally consistent? Is it this nonsense situation? Give me examples of behaviors leading to chosen places in the spec. This is very helpful when understanding what is actually happening in the protocols we wrote. Can my design result in a deadlock? Or do all the safety invariants hold? In this simple example here, we have implemented a simple bank model, and the invariant we gave was no user should ever have negative amount of money in the bank. And we asked Quint, can you check if that can happen? Quint says, yes, that can happen. Bob can have -1, and here are the steps that lead to it. And Quint would also, if we ask for it, show us what exact actions and what exact non-deterministic choices led to this situation. How does Quint do that? And this is going to be the only slightly technical slide in the talk. So we said already the problem is this large state space, and the task is to explore all possible states of the protocol on a very large graph. Quint semantics is based on temporal logic of actions, a logic for describing distributed systems developed already some decades ago by Leslie Lamport. In order to analyze the state space, Quint uses model checkers Apalache and TLC, and they are amazing because they guarantee that they're going to inspect every state. Their problem is that they may be very slow. That's why Quint also has a simulator for quick feedback while we are developing our specification. So if before Quint we were here in the pipeline, now we move here, where we start from a combination of English specification and Quint. We keep English for intuition, and we have Quint for precision. And with the help of Quint tools, we also get this self-improvement loop on the level of spec. So now we iterate on the spec, and this makes our overall engineering process faster because we iterate on the higher level of abstraction. And this all looks great, but you may already wonder, okay, even if we are confident that our spec is correct, what does it tell us about the code? After all, it is still this LLM-generated process, so do we know anything about the code? Quint glues the code to the spec by generating lots of automatically generated tests that bind the spec to the code. And in that way, in the limit, turns this squiggly line into a straight one. So overall, what does spec-driven development with Quint bring us? It helps us thinking about the specs. So if before we were working on a white piece of paper or a Notion document on a whiteboard, writing English and thinking about how it happens going by hand, Quint is our dynamic assistant in showing us what could possibly go wrong and what are the properties of the spec we have currently. By binding the spec to the code, it makes our code generation step more reliable. Once we are done with the spec, using model checkers, we can validate if what we got is what we wanted. And because of all these three things, we get higher engineering velocity, because we iterate on a higher level of abstraction, and because we have more trust in our implementation, so we can easily add more features. So this is our vision for the future of software engineering. Code is still the king, because in the end, it is the code that gets executed. But spec is the queen, this powerful dynamic figure that makes sure your code is safe and sound. And if that's the future that interests you, or better yet, excites you, let's talk details. At any coffee break, at an open spec session in 15 minutes in the workshop room, or just follow Quint on Quint's website or in a Telegram group where there are already around 100 users helping each other, beginning with Quint, or also getting help from the team, from the Quint team. Thank you a lot.